Okay. So content, use FSP files. Basically, what are the necessary files you need to have in your build? Use UPD for FSP configuration. What is the implementation coreboot to be able to use UPD? And then I'm gonna quickly walk through FSP phases and then talk about what needs to be done in terms of integration for auto phase to be successfully executed. Then I'll talk about a few specific things that I learned from the project. And also there's some issues I will talk about that we found from using FSP from Skylake. So and then I have a picture of memory map of Skylake using FSP, and then we'll do some QA if we have time. So use FSP files. So before that, Skylake FSP complies to FSP architecture version 1.1. The newer version is FSP 2.0, as Giri talked about yesterday, and then NJ talked about the first day. So starting Apollo Lake, they're using FSP 2.0, but Braswell and Skylake are using FSP 1.1. But I'm talking about the Skylake, so it's 1.1 here. But a lot of the integration mechanism actually applies to 2.0 as well. So needed file in your coreboot build. There are two files that you must have. FSP.fd is the FSP binary. FSP UPD VPD.h is the the header file that you have to have, and which contains the VPD UPD data structures and then related definitions. The FSP BSF file is not required for the build, but it's for you to use the BCT2 and config the binary, some static values. Enable FSP usage. There are a few config flags you need to worry about and config in the build. At least on those here. So config FSP file, the first one actually will have the path to the binary. Config FSP include path will have the path to the FSP UPD VPD.h. And there's the FSP location, the FSP cache size. You have to specify that. Of course, config have FSP bin. And then use FSP 1.1, you have to set yes to those two. FSP integration guide is a document that's part of the FSP download package from Intel. You want to read the document to understand the generic bootloader requirement for integration, not specific to coreboot, but it's a general bootloader. And then some SoC, and then the SoC configuration definitions. Basically, it will tell you what all the UPDs are doing and what those options are, and what values you can set those values or those options to. Use UPD. FSP UPD's interface, as you might know already, for bootloader to apply SoC configurations to FSP in phases in order to support your platform. UPD do have default, so you want to refer to integration guide for those default values. If you like the default, okay, you probably don't want to touch it. How we implement in coreboot to use UPD, for FSP to consume. We use existing coreboot framework to do that, right? So chip.h will supply the SoC configurations, which maps to the FSP UPDs. If you look at the chip.h under SoC Skylake, there's a big list of configurations that's actually mapping to the FSP UPDs. I have an example there. And where do you config those items? Device tree.cb, of course. So that's where the configuration are actually valued per board requirement. One example is the Google large device tree.cb, and that's where you register. For example, you register enable Zadia equal 1. So that's where you set the value that you want for your platform. But this is not like complete, and those value are not automatically used by FSP and just working. There's a backend functions that doing the passing. So we'll cover that in the later slides when we talk about phases. Any questions so far? Yeah. Okay, now we'll walk through a little bit on the FSP phases and then talk about things that need to be done. So FSP temporary mini, this is the phase that's primarily doing cache as RAM in it. However, with Skylake, we we don't actually use that phase to do carrying. Coreboot does the cache as RAM initialization in itself, and then would then call the FSP temporary init for the rest of its settings, because there's some other very early SoC configurations that's in that phase. We don't want to lose that. So the code resides in cache as RAM init, cache as RAM and C file within FSP 1.1 driver. And the code snippet is here. And then there's one critical flag you need to set, which is config skip FSP car. I think with Skylake, there's no option. You have to set that one to yes to be able to use the coreboot implementation of cache as RAM init. And there's two other configs you have to config. One is providing the car base, and the other one is providing the car size that you need.
And those need to match what's in the FSP. So
no, those you set in coreboot, and you pass that to FSP through UPDs.
Okay.
The base and there's two UPDs for the FSP.
Okay.
Yeah. Okay, FSP memory. This is the phase that's primarily doing memory training and the configuration. So the mechanism is prior to calling this phase, coreboot will update its related UPDs. Remember, talk about having options in the chip directory and device tree. So this is where those settings are honored and get utilized. So we look at the ROM stage.c under Skylake. There's a function called SoC memory init params. So that's where the UPDs gets updated with either a hardcore value, like we think, okay, this hardcore is good enough, or it's updated by the config values that we set in device tree.cb file. And also in the ROM stage.c under a specific board directory, there's a similar function called main board memory init params. That's also passing some input to the UPD. For example, SPD data is passed in that function for the board. Okay, so
So just on this one, we're hard coding the MMIO size, but we're doing that in a chipset specific location and not in a board location. So can we? I guess we can update that later in the board location if we want a different one.
You have to if you want to do that, you need to get rid of this line, and then I don't know the sequence of each.
The sequence is that
main board after.
Main board is after, so you can override it.
Okay.
Great.
Okay. Yep. If you want to look at the actual caller function for FSP memory init, you can refer to the RAM init.c under FSP 1.1 driver. So that's where you see, all those hooks are callbacks of, are called, and then you actually call into FSP memory function. So the next phase is FSP silicon init. It's primarily doing the rest of the SoC configuration except for the memory controller, and this is supposed to run in RAM stage. The mechanism is actually same. You prior to code interface, the code will update relative UPDs, and then the corresponding configs in the device tree.cb are utilized here. The file is chip.c under SoC Skylake, and the function is SoC silicon init params. It's about doing the same thing. You update UPDs from whatever variable you want. Some are hardcore and some are from your config device tree.cb. And also on the board directory, you have the RAM stage.c that has a similar function to do the main board silicon init params. And I think that's it could be a placeholder. Right now I think it's when we're doing GPL, we're calling GPL configuration in that function for main board. So for the caller function for FSP silicon init, also you can look at FSP 1.1 RAM stage.c, and that's where you actually call into the FSP silicon init with, of course, the parameters. So in terms of integration for those two phases, basically it's all about setting. It's all about having the configuration in chip edge and setting values in device tree.cb, and of course have the lines in respective functions to pass into FSP.
So is there any way to still use the default values from the FSP?
If you don't override in device 2 IP, you're using the default because the code is actually copy the whole UBD structure into and update whatever you want to update.
Okay, but with this right now, is there a way without deleting this that we can use the defaults?
I think if you have that defined in the chip edge, unless if you don't set in device 2B, you're actually giving 0.
Right.
Right. So that could be a problem. So my suggestion is if you have an option in the chip edge, you better initialize it in the device 2.cp. Okay. Otherwise, you could use 0. You're using 0 for all these options.
Right.
That might or might be not the default. Right.
Right.
Yeah.
Okay.
So Martin, to use the FSP, you can pass the UBD as a null pointer. And internally FSP can read the defaults and use it. If you don't want this code either, the other option is you can just skip all these things using configuration.
Okay. Well, just with the FSP 1.0, we specifically made it so that 0 was use the default, which I admit was confusing, but it allowed that option. So I was just wondering, was that removed?
In some cases, I mean, that depends on the parameters of individual policies. But overall, instead of leaning to each specific parameter, we generally said that the function when you pass silicon of the UPD pointer, if you pass a null value, that means bootloader wants the FSP to use the default. Okay. So bootloader, I mean, in some scenarios, you don't even need this piece of code to do anything. But you can just say pass a null. You already used the static configuration. Okay. So it minimizes the bootloader code. Right. So Robbie, one question on the hard-coded one is because the ISH enable as an example. Right? Is this because different default than what it is there?
It's a choice of platform. I think for Skylake, at least for Chromebook, we don't use ISH at all.
So it's different default.
I think FSP default is 1 because the REPs are using that. So we want to change that for Skylake Chromebooks. That could be a problem because there could be other platform out there that you use ISH. One thing I want to talk about is you might want to ask, hey, I have a I have a board and I need a configuration option, and I don't find that in chip.edge. What should I do, right? So the way to do that is you want to look into the FSP UBD UBD.edge file, as well as the integration guide to see if the option you need is there or not. Because UBDs could be long, many, and we don't necessarily put all the UBD in the chip.edge file for you to configure, right? So if you find the configuration you need in the UBD in the UBD list, perfect. What you do is add to chip.edge, configure that in device tree, and add specific lines into respective functions. Depends on what phase that UBD belongs to. That's the ideal case. If you don't find the configuration option that's provided by FSP, you want to send a request to Intel, ask for adding.
Gotcha.
Also, the FSP UBD uses the comments in a box format. Integration guide is extracting from the code. So if you're using the code, you already have the documentation. You want to go back to your documentation.
Just another question.
Sure.
So some very simple examples. So is there anything, any option you could set that we couldn't do with device tree? Because I'm asking myself, do we really need the mainboard versions of these functions? Couldn't we just take everything from device tree and in the mainboard directory just use device tree and not use any extra functions?
You're talking about whether do we need to have the mainboard functions there? Yeah. That's true. Well, actually, in Skylake, the mainboard silicon in params is actually a placeholder, and we don't actually pass in any config values in that function to FSP.
But that would be the only way to override one of these hard
Yeah.
values.
Yeah, but we could just in the SOC directory just if I hard code just always use it device tree.
Yeah, that's true.
Yeah, but that's the case where one said, hey, for some reason we set a hardcode value in the chip in the the SOC file, but you can override that in the main board, right? So next phase is FSP notify. So this phase is registered as a boosted callbacks in coreboot. Currently, there's not input is required for that phase to be successfully executed. There are two callbacks. One is the after PCI enumeration. So this callback is upon this event, I think, this state. This is supposed to call after PCI enumeration, but before execution of third-party code such as options. I'm not very sure how this is enforced in coreboot. But anyway, currently nothing is implemented in FSP for this phase. Basically, call into that and just return without doing nothing. The second callback is ready to boot. It's upon ready to boot. This is supposed to call before you giving control to OS booting. So in this phase, FSP doing things like locking chips registers, or sending the NF post messages to ME. So like finalizing the chipset in the last minute, right, before you put the OS. And no input is required, no integration is required for this phase. And the code resides in FSP util.c under FSP 1.1 driver. You can refer to that code snippet. Okay. So we've just finished walking through the FSP phases. Now I want to talk about a few specific things that we learned from the project. Some are related to FSP integration, some are not. Okay, so SPD data is passed to FSP memory also through UPD. The SPD data connection is coreboot's responsibility. Basically, you either provide a fixed SPD data hex file, or you let coreboot to go and read SPD data from DIMMs through SMBus protocol. But the data connection is coreboot's responsibility. GPL has a big thing. GPL configuration is handled in coreboot entirely and not relying on FSP. FSP does have the capability of program GPLs, but we decided to not use that because we want to have the GPL configuration in coreboot for flexibility. And then for integration, you need to have, for every board, you need to have a GPL setting data file, reside in the board directory. One example is the Google Large GPL.h file. For your board, you need to have your a similar file like that. Next one is the video option. VBIOS is no longer used. I think that we starting brass. Well, we are already dropping that. So graphics PIM used to be called GOP. It's the new module to initialize graphics. The only input that below the coreboot needs to provide is the vbt.bim file. That's the only file that every board needs to provide. There's one config GOP support. You have to set that one to yes. There's no option. You have to set on the yes to be able to use the graphics PIM, because we drop VBIOS support. And then just functions is in the code resides in vp.c on the FSP 1.1 driver. You can look at it.
So one clarification of the
yeah.
Only for your board is using graphics. If you want to use extended graphics, you still
that's true. That's true. Yeah.
Yeah, I'm currently replacing VBIOS with something else. So no problem.
So this is just abstractly PA-GOP is just simplifying the code. In this case, you don't need to go into the dictionary and simplify and guess the display out.
Script MPNI, I think we talked a little bit about that yesterday from Gary's presentation. So FSP contains a native MPNI driver and then service and protocols. But it also provides a UPD called skip MPNI. So code will utilize that to basically bypass the MPNI driver from FSP and use Coreboot's own MPNI driver. The place to set that is, of course, in device tree, and you register that contribution to 1. FSP boot time. Boot time is critical. We always want to make sure that it meet our requirement. So the timestamp logging is already placed around all the FSP phases. For example, if you look at the RAM stage.c under FSP 1.1 driver, we have like before and after FSP Silicon init, they're already timestamp added. So once you boot it, you can run cp memory-t, and that you can dump timestamps, and you can see the time consumption of every phases. One example is taken from Google Lars board. So here, if you look at the last line, FSP Silicon init, the consumption, the boot time for that is 33 millisecond. So you can use that as a reference for your Skylake board. If you see a way larger number than that, you might have a problem. Something is getting slower. So some issues we found from using FSP. There are quite a few. I won't be able to list all those, but I just pick things off of my mind. FSP size is big. I think on Skylake, the FSP binary release build is 0.5 meg. The debug build, of course, that's not released yet, is a little bit over 1 meg. So that could be a problem because you have FSP copies in the ROM in the RO section, RW and RB. Basically, you have 3 copies of that in your flash. So if size big, you could, and of course you will have ME binary, you'd have microcode and other blobs, and potentially you could you could not fit into the flash chip you have. So that's an issue. We did some optimization to try to reduce the size. FSP boot time could be long, especially at the early phase with the early version of FSP. I could consume like a couple hundred milliseconds or even longer. So we always need to go and then debug and then find a place where it consumes most of the time, and then whether it's some mismatch thing from the sync up, or it's a unnecessary delay, or it's handshake between coreboot and ME gets a problem. So we have to always optimize that to reduce the boot time. I think on Skylake we're okay there. So the other one is FSP is the issue that we found, as Aaron pointed out, and then give solutions. So FSP touches MTRR and doesn't restore its state. I think it's FSP Silicon, and does not restore its state to the coreboot setup before calling the FSP phase. So in general, the learning from that is FSP will consume resources, right? But FSP should free those resources and return those resources to the bootloader after it finishes the job, because that's really a bootloader's resources. So I think we take that learnings and then implement that into FSP and going forward. So the other one is also is FSP resets the system from within itself. So this is very bad, right? Bootloader has no idea what has just happened. So one scenario is it destroyed the boot mode from coreboot, and could jeopardize as resume or recovery mode, right? Because you do code reset and then you start from coreboot. So we take the learning there, and then I think from FSP 2.0, FSP will expose the reset request to bootloader instead of blindly performing the reset from itself. So it leaves to the choice to coreboot to make the actions. The other problem we have struggled quite a bit for Skylake is the FSP UVDs are not clearly classified in terms of whether it belongs to FSP Memory init, whether it belongs to FSP Silicon init, right? A lot of stuff are actually in the beginning are put into FSP Memory init. So these were critical when this was particularly critical when the FSP Memory init was not supported by the RW section. You cannot do memory init rewrapping. So because if you cannot do that, you have all the Silicon init configuration in the memory, you actually cannot update it. You cannot actually do rewrite update, right? So we struggle that, and then I think going forward we are always paying attention to the FSP team, like working with them to make sure, hey, to look at all the UBDs to make sure we have clarifications for all the items, and try to make sure for FSP memory we only have memory-related configurations. Because I think the philosophy of ROM stage is just to get the memory up and running, and then provide the memory environment for RAM stage.
And in some cases, we do have more than just one for memory. Few things are like storage, data, property saving, because those need to be done sooner, performance and that's why we went to classification.
Yep.
Found some things can be done later. If we have to do earlier, reducing some minor factors.
Yep. Oh, any question?
So one thing when Robbie mentioned about the size and space optimization, right? In the past, we had a debug is one. And that's one of the benefits in the FSP Controller where we get explicitly space one. Since you have three components, you can pick your debug in memory.
Yeah.
Only in the memory of the debug model. So you can just one plus other.
Yeah.
You don't have to take all of the pieces in the debug mode. That should benefit from the size constraints. You have multiple copies around sometimes.
Right, because with Skylake it's one big pop, so it's either small or big. But with FS2LO, you can choose like each blobs, right? But we still don't release the debug image yet, so that's a.
No, we want to.
Yeah. Right.
Still don't FSP with WinDBK, or is it new tools now?
You mean
build
with GCC? Yeah.
What do you all?
We default use Visual Studio. But if a Chrome user is using the GCC, with NTGO, the size is pretty much comparable now. In the past, like without NTGO and GCC, we had a huge size. Still, we see that the size is the minimum. So we tried all these things so far on this is in some benefit, but we do support all the three components.
Yeah, and then during the FSP integration and all, special thanks to Duncan and Aaron for pointing out a lot of FSP issues and give suggestion directions. So that's okay. This is a picture of the memory mapping with Skylake using FSP, of course. And then if you look at, I'm only listing the stuff below 4 gig. So if you look at from 4 gig downwards, you have the all the different bars and regions, and then you have the PCI-Express MMIO space, and then you have the ME memory UMA, and then of course you have the graphics memory, DSM and GSM, and the TSEC. And then there are a few new regions that's added with Skylake, the PRM, IoT, PTT. So the toolroom is actually right below TTT, right? So that's where the bootloader, the available memory for bootloader, and then the first region that's been used as FSP bootloader toolroom region is where we put CB memory root in there. And then the very first region after that is actually FSP reserved range, and then the CB memory root actually put ID there and then reserve that region, and then rest of stuff are available memory for system to use. This is just with FSP, you would see those two memory regions there. That's special.
In the 1.0 previous implementations, we had FSP reserved CB memory, and this one of the discussions with Aaron and so we want the CB memory to be the primary.
Yeah.
So the FSP region is covered under the same. So that's why we added this as an architecture. 1.1 already has this.
Yeah. And then the CB memory top is the function in coreboot that actually walks through down all this hardware registers to get to the bottom of the toolroom, and use that as the top address for CB memory root. Okay, there's some links. I guess Kiri's slide has more links than I do. So FSP download, and then the architect specs for 1.1, 2.0. Okay, so I guess any other questions? That's quite straightforward.
Thank you.
Yeah, thank you.